All right, we are live. Oh, let's see. Zoom does not like the fact that I'm muted. Guess I should change that. Okay, perfect. All right. Can everyone confirm they can hear me all right? Let's see. Not seeing anything in the chat, so I'm going to give people a moment to make sure that I am audible. Okay, perfect. Looks like we are good to go then. All right, yeah, so hopefully the contest went well for everyone. I'm seeing that a lot of people had A and B and then ended up having some trouble with C. Some people had some issues with A, which makes sense. It was kind of a weird one. But yeah, I mean, overall, this contest had a pretty smooth difficulty curve. A and B may be relatively similar in difficulty, but then C a lot harder than B, D a lot harder than C, E a lot harder than D. And so hopefully all of these solutions should be helpful to at least some of you. So as usual, we're going to go through the problems one by one in order. And then and so we'll start with A and then go to B, then C, then D, then E. And then if you have questions, please feel free to put them in the chat anytime, and I will go over them as soon as I see them. All right, great. So first problem is, as at in two subsequences, we have an array of n integers, which could be negative, and we have to split it into two non-empty subsequences A and B. We're trying to maximize f of A plus f of B, where f of x is the average of subsequence x. So in other words, we're trying to maximize the sum of the averages of the subsequences. Oh, and Clapdota says, author of E here, curious what you all thought about it. Yeah, I thought it was a fun problem. I'll talk about it more once we get there, but that'll be a couple of minutes. Okay, so let's talk about the solution to A. All right, so here's the key idea. We want to put larger elements in smaller subsequences. And the idea here is, let's say that we have some really big value in, like, I don't know, let's say that A sub 1 is really large. Then, if we put A sub 1 in a small subsequence, then we're going to, let's say we put it in a subsequence by itself, then that subsequence is just going to have length 1, and so A1 is just going to be divided by 1. If we put it in a subsequence of length 2, then we're going to be dividing it by 2 when we compute the average of that subsequence, and so on. But basically, since A1 is really large, then we're going to want to divide it by the smallest possible number to make sure that it stays large. And so, more generally, let's say that the subsequences have length k and n minus k. So the first one is going to be k elements, and the second one will just be the rest. And let's also say that k is the shorter one, so with k less than or equal to n minus k. Then the claim is that we're going to put the largest k elements in the subsequence of length k. And so I'm not going to write out the proof especially formally, but the general idea is, let's say that the sequence is sorted in descending order without loss of generality. Actually, let's say that it's in ascending order, because that's how we do it in my solution. So A1 is less than A2 is less than A3, all the way up to AN. Then the idea is that we're summing up k elements divided by k and n minus k elements divided by n minus k. And since a number divided by k is larger than that number divided by n minus k, we're going to divide the largest numbers by k. All right, cool. So, and the same logic works when we're dealing with negative numbers, except with the negative numbers, we're going to want to divide them by with the really negative numbers, we're going to want to divide them by something larger to sort of decrease the extent to which they harm the answer. All right. So what this means is that we only have n possible divisions to consider. After we sort the array, then we can just test out, okay, what happens if we put A1 in one subsequence and A2 through n in the other? We can test what happens if we put these two in the first one and these n-2 in the second. What happens if we put these three in the first one and the remaining ones in the second, and so on. So I can show you my code. So what I do is I read in the sequence and then I sort it, and then I maintain sum 1 and sum 2. And sum 1 is going to be the sum of like the first elements, and sum 2 is going to be the sum of the last. And so initially I start when we like put every element in the second subsequence. And so then for each of the first n-1 elements, in order to make sure that both subsequences are not empty, I remove this element from the right subsequence and I add it to the left. And then I try this as the answer. And so if we just added a of I where I is 0 indexed, then the first sequence has length I plus 1 and the second has length n minus I minus 1. And so I set the answer to the maximum of the answer and then the current value, and then I print the answer when we're done. All right. Now, a number of you guys might have had some TLE issues on this one, I did when I first submitted it. And the issue here is it turns out that I actually just learned this today, that reading in doubles in C++ is really slow. And so when I made this an array of doubles, which is VD in my template, that got TLE. And so it turned out that reading all of these as longs rather than doubles significantly improved the speed of my program. Went from about 1,000 milliseconds down to about 90. So that's what I would recommend. And Neil says you can just take the largest element and all the remaining elements. Is that provably correct? I guess it probably is. I know I didn't go that. I ended up not proving anything stronger than this claim in the contest, and then I just moved on. But let me think about how you would prove that. So let's see. Yeah, it makes some intuitive sense, but oh yeah, that makes sense. Okay, so what Neil says in the chat is, so after we prove this fact, now let's say that we have the the sequence A1, A2, A3 up to AK, and AK plus 1, AK plus 2 up to A sub n. Then when we move A sub k plus 1, then when we move the last element of this sequence to this sequence, and so we instead have A1, A2 up to AK plus 1 and AK plus 2, AK plus 3 up to AN, then both of these averages are going to increase because AK plus 1 is going to increase the average of this sequence and decrease the average of this sequence. And so that and when AK plus 1 is in this sequence, then it's sort of bringing down the average because it's the smallest element in the sequence. And so we can keep doing this sort of step where we move the smallest element in this sequence to this sequence until all we're left with is A sub n. And so that gets us, and so then we can just compute the solution for that sequence. So that's something that we can do to make this a little simpler. And if we wanted to write the code like that, what we would do is we would just say sum equals 0, and then for I n minus 1, sum plus equals a of I, and then divide by n minus 1 because we're averaging the first n minus 1 elements, and then just add the last element. Okay. Yeah, nice solution. Thanks for sharing, Neil. Okay. Awesome. Yeah, so that's problem A. Let's see, are there any other questions in the chat? Okay, I don't see anything. So let's move on to problem B. All right, so momen and k subarrays. We have an array of n distinct integers, and we have to sort it in non-decreasing order by performing the following operations in order exactly once. So first we're going to split the array into exactly k non-empty subarrays such that each element belongs to exactly one subarray. Then we get to reorder these subarrays arbitrarily, and then we have to merge the subarrays in their new order. And so we have to figure out whether there's a way to sort the array by performing these operations. Okay. So let's think about when we're going, let's think about the problem like this. I'm gonna pull up my notes. So let's look at the first sample input. So we have 6, 3, 4, 2, 1. And so let's think about when we're going, let's think about it as if we're placing dividers between any two subarrays. So for example, in our eventual answer, we end up placing the dividers like so. And so let's think about splitting the array or partitioning the array into subarrays, and let's think about where we need to place those dividers. And what I'm going to claim is that suppose a of I plus 1 does not appear immediately after a of I in the final array. Then there must be a divider between I and I plus 1. And so for example, here 3 does not appear immediately after 6 in our final subarray, or in our final array, and we can see that quite quickly because 3 is less than 6. And so there's a divider between 6 and 3 here, i.e. 6 and 3 are going to be in different subarrays. And this claim can be proven pretty quickly. The idea here is that if these two elements aren't supposed to be next to each other and we don't place a divider between them, then even when we finish our process, they're still going to be next to each other when they shouldn't be. And so, for example, if we were to erase this divider here, then no matter how we reorder the subarrays, 6 and 3 would always be next to each other, which is bad, because then the array wouldn't be sorted. Okay. So then the other claim that I'm going to make is that we don't need any more dividers. So no more dividers are needed. And this one I'm not going to go through formal proof, but you can see it pretty intuitively. As soon as we sort of split into these components that all go next to each other in the final array, then we're going to be able to rearrange them in order to get a valid sorted array. Okay. The other thing to realize is that if we've split the array into fewer than k segments, then the requirement that we have to split the array into exactly k subarrays is not going to be a problem for us, because if we have so like let's say for example here we have 4 segments, we can just throw in random dividers to create a fifth if we were asked to set k to 5. So like for example, we could just throw in another divider here and we'd still be able to sort the array. In general, splitting them into more subarrays is not going to be a problem, because if we create a split that we don't want to have, if we have a single subarray and then that doesn't need to be split, but then we split it anyway, we can just put the two parts next to each other in the end, and so it's not going to be a problem. All right, so ultimately what we can do is we can just count the number of dividers that we're going to need. And if that's going to split us into most k segments, then the answer is yes, and otherwise the answer is no. And some people have mentioned in the chat that there's some questions about whether you can just count the number of times where a of I plus 1 is less than a of I, and the reason that doesn't work is that if we had, for example, if our input array is 1, 3, 2. Then what you're suggesting would only require a divider here. We put 1 and 3 in one array and then 2 in the other. But in fact, that doesn't work, because no matter how we arrange it, 1 and 3 are going to be next to each other when, in fact, we should have 2 between them. So what we actually have to do is just put all 3 of them in their own array. And then we can just sort them naturally. So I'll show you my code real quick. Essentially what I do is first I read in the array, and then the way I compute the final array, which I know there are a couple of ways to do this. You might have your own way, but the way I did this was by performing coordinate compression, which is a pretty common technique that you see in segment tree problems, but it also can be helpful in some simpler problems such as this one. And so what I do is I maintain a set of all the values appearing in the array, and because it's a set, it's automatically sorted. And so then I maintain this compression map, and I iterate over the array in sorted order, and I set the component of each node, or of each I set the component of each value to the current size of our compression array. And this is going to maintain the ordering while reindexing the values with 0 to n-1. And so, for example, in our input array 6, 3, 4, 2, 1, that ends up getting transformed to 4, 2, 3, 1, 0. Because 1 is the smallest value, it gets 0. 2 is the second smallest value, it gets 1. 3 is the third smallest value, so it gets 2, and so on. And so after I compress it, then after compressing, then I plus 1 is going to appear after I. And so I can check whether a sub I appears, or a sub I plus 1 appears right after a sub I in the final array by checking if a sub I plus 1 is equal to a sub I plus 1. And by doing that, I store the required number of subarrays, and if it's at most k, I print yes, and otherwise I print no. Okay, so let's see if there are questions in the chat. Let's see, will the failed tests become viewable? Yes, I'm not sure when, but eventually you'll be able to see the results on any test cases you failed, probably after system testing is finished. Purple Crayon asks, isn't comp of A equals size of comp undefined behavior? No, so here size of comp is defined to be whatever it is before A is inserted. Let's see, Bhaskar asks, can you explain compression technique again? Yeah, so basically the idea here is, so the first thing you do for coordinate compression is, so step 1, create a set vals containing the unique entries of the array. And so in the sample input, vals is going to be 1, 2, 3, 4, 6. And then step 2 is to create a compression map that maps these values to 0 through n-1. And the idea is that I'm going to use this traverse loop through vals, which in my template, if you haven't seen it already, is essentially for auto A and X, so essentially for every value in our set. And it's going to iterate, and this iterates through the set in sorted order because sets are always sorted. Then you can, so essentially I'll show you my comp map. So the first number we get to is 1, and currently the size of comp is 0. So 1 goes to 0. Then the next value in vals is 2, and currently the size of comp is 1, so 2 gets 1. And so similarly, 3 gets 2, 4 gets 3, and then 6 gets 4. And then I just set all the values in A to the result of the compression map. And you'll see this again, I use the same technique in problem D. Yeah, so let's see. So a couple of questions in here. Let's see, is there a Python equivalent to this solution? Yeah, I'm not super familiar with Python. I'm not sure what their equivalent of a set is. I know for a map you can use a dictionary in Python. But yeah, this is something you should be able to implement in Python. Lin Zhang says we can also save a sub i's original position and sort it. Yeah, that's correct. So we could create a new array of pairs of the form a sub I comma I, and we could sort this array, and then we'd be able to figure out whether I and I plus 1 are next to each other in the final array. So that's how you could do it by sorting. Sarav asks, what's your typing speed? Varies from day to day, but on average, I'd guess around 120 words per minute. Joseph asks, can you share your template? Yeah, I put a link to it in the description of my screencast when I upload it. But if you want to see it real quick, I'll put a link to my submission for A in the chat. Or actually, I guess this is my submission for B. And you can see my template in here. Someone says you can write set vals of all and pass all of A as an argument. Yeah, that's a nice way. That's a nice way to do it. It might make this a little easier. Okay, let's see. A lot of comments in here. I apologize if I'm missing a few of them. Can you use binary search? Not that I'm aware of. Let's see. What editor do you use? I use Vim. Okay. So yeah, and I should note, like, and a lot of people found this this just sorting method easier to think of than coordinate compression. The main reason I thought to use coordinate compression here is because it's something that I've seen a lot when I've been solving higher level segment tree problems. And again, it is something that we'll actually sort of need to use in problem D. And so it's just kind of a natural thing I think of whenever I want to get the values of an array into this nicer format. Let's see, people are telling me to look at Tor's solution to B, so I guess I will do that. Let's see. Okay, yeah, so Tor's is doing essentially what the equivalent of the sorting solution. So he's reading in the array, and then he's building this order, and in order to sort it, he's using what's called a lambda expression, where essentially he's placing I before j if a sub I is less than a sub j. And from there, and so that bit essentially gives the order array, and from there the solution is pretty similar to what I'm doing. Can you tell what iota does? Let's see. I'm guessing that what it's doing is it's just filling this array with 0, 1 up to n-1. But I actually haven't seen this command before, so I'll take a look. Yeah, it just fills a range with sequentially increasing values. And so here it sets the first value to 0, the next value to 1, and so on. And since order has length n, it's going to set it to the values 0 through n-1. Bhaskar asks, if values are repeated, then does this compression technique work? Yes, it does. And that's the really nice thing about it, is that, and that's why it's going to be, and that's part of why it's going to be so useful in D. All right. So let's go ahead and move on to problem C. And if people have more questions about this one, I will be happy to take them at the end. All right, so we have two players playing a game, and they're going to make an array A of n non-negative integers where every element is less than 2 to the k. And we want to count the number of arrays where A1 and A2 and A3 and up to AN is greater than or equal to A1 XOR A2 XOR A3 XOR AN. And some people are asking, will my solution work if the elements of the array are not unique? No, but so it won't. However, the coordinate compression part is not what's going to fail. It's just you're going to need a slightly different idea. Okay. So yeah, I'm gonna move on to C now, but I'm happy to take more just so that because I know a lot of people have questions about it, but I'm happy to take more questions about A and B later if people still have them. Okay, so we want to count the number of arrays where their AND is greater than or equal to their XOR. Okay, so what I'm going to do here is I'm going to do casework on the parity of n. And if you haven't seen this word before, the parity of n means whether n is even or odd. And so, and the reason that we would think to do that is if n is odd, if n is odd, then whenever a bit is set in all of these values, then this AND is going to be 1, and if n is odd, then the XOR is going to be 1 too, because recall that the XOR is 1 in a certain bit if that bit appears in an odd number of these positions. While on the other hand, if n is even, then whenever a bit appears in the AND, then it's going to be a 0 in the XOR. And so the parity of n sort of affects how values in this AND expression are going to affect values in this XOR one. And so that's why we're working with the parity of n. All right, so let's say case 1, n is odd. And so let's think about it. Let's think about just a single bit. And so if a bit appears in all a sub I, then it's going to contain, then the AND is going to contain a 1, because AND is just 1 if and only if a bit appears in all of the a sub I. And the XOR, which I'm going to use the caret just like in C++, is going to also get a 1, because a sub 1 XOR, or because the XOR is 1 if an odd number of a sub I have the bit, and since n is odd, that's going to be true when a bit appears in all a sub I. And so if a bit appears in an odd number of a sub I, but not all a sub I, then since it doesn't appear in all a sub I, the AND is going to be 0, and the XOR is going to be 1. If a bit appears in an even number of a sub I, then the AND is going to be 0, and the XOR is also going to be 0. And that's because it appears in an even number of these a sub I, and so the XOR is 0. And so this case is bad because if the AND is going to if the AND is less than the XOR, then this inequality is going to be violated. And meanwhile, we can see that it's never going to be possible in this case for the AND to be greater than the XOR just by looking at all three of these cases. So what that means is we need one of these two cases to appear in every single bit, in all k bits. And so we can count the number of ways for a bit to appear in all a sub I. There's just one way for that to happen. It has to be 1 everywhere. Or for a bit to appear in an even number of a sub I. And we can compute that using the choose function, because if it appears in 0 a sub I, then there's n choose 0 ways. If it appears in 2 of them, then there's n choose 2 ways to pick which 2 it's going to appear in. If it appears in 4, then there's n choose 4 ways, and so on. And so we can compute the number of ways for this to work by summing up n choose 0 plus n choose 2 plus and so on. Okay, so let's talk about case 2 where n is even. Now, the lucky thing here is that these two cases actually work out the same, because they're not really dependent on the value of n. So it's still the case that if a bit doesn't appear in all of the a sub I, then AND is going to be 0, but XOR is going to be 1 only if the XOR will be 1 only if only if there's an odd number of positions where this bit appears. But now, if a bit appears in all a sub I, then AND is going to be 1 because it's in all of them, and XOR is going to be 0 because it's in an even number of a sub I. And so, in this case, it's actually possible for AND to be greater than for the AND to be greater than the XOR. And so, in particular, if AND is greater than XOR in one position, then in all of the smaller positions, the values don't matter, because we know that if AND has a 1, XOR has 0 in one bit, then it's going to be greater than AND will be greater than XOR no matter what the values in the smaller bits turn out to be. And so what I'm going to do here is I'm going to do dp. I'm going to build the sequence starting with the largest bit. And our state is going to have 2 dimensions. So it's going to be, our dp is going to have format k plus 1 and 2, where dp of I of j is the number of ways to build the largest I bits of all elements, such that if j is 0, then the AND value is equal to the XOR value, while if j is 1, the AND value is greater than the XOR value. And the idea here is that so we can use this. So we can transition in this case if n or in either if j is 0 or 1, and then afterwards n is, or our and is definitely going to be greater than our XOR. So that means that both of these things are going to go from j equals 0 or j equals 1 to j equals 1. In this case, this is going to make XOR greater than and if and is not already greater than XOR. And so this is only a valid transition if j is 1. And then this thing is just a valid transition in either case. And in order to make the implementation a little bit shorter, I actually use a similar DP approach in the first case too. And the only change that you have to make is this case no longer leads and to be greater than XOR. So essentially, you're never going to get to j equals 1 in this first case. So I'll show you how I implement this, which might make a little more sense. So let's see. So initially I create odd and even, which are integer or mod-ins representing the number of ways to create an odd number, or to put a bit in an odd number of positions that isn't all of them, and then an even number of positions, but that isn't all n of them. And I build that just using my choose function. And then I have this DP array. And initially, the number of ways to fill the first 0 bits such that the and the XOR are the same as 1. And then for I from 0 through k, or for all k bits, so I just perform all of the various transitions. And so the first transition I handle is this one. And that here, we can't do this if and XOR are the same, because then XOR will be greater than and. But if they already are, but if x and is greater, that's when DP that's when we're already in state 1. And so we transition to the next state 1 from the current state 1, and there are odd ways to do that. Next, I handle this case. And this case we can do in either state because it's not going to affect which one is greater. And so that gives us even ways to transition from 1 to 1, and even ways to transition from 0 to 0. And finally, I handle this case. So first of all, if and is already greater than or equal or greater than XOR, then that's going to be maintained. So that gives us one way to transition from 1 to 1. But if n is not already greater than XOR, then it depends on, then this is where whether n is even or odd matters. If n is odd, then we're still not going to be greater than and is still not going to be greater than XOR, and so j is going to stay as 0. Our second dimension stays as 0. So we go from 0 to 0. But if n is even, then as we see here, and is going to become greater than XOR. So we're going to transition from 0 to 1. And then finally, I just print out the results when we get to when we get to the kth bit when we're done. All right, awesome. So let's see if there are any questions. Let's see, I see a question that asks, why are you taking two cases of odd and even? The reason I'm doing that is we have this sort of special case where and is 1, and that's only when all the elements are, or when all the elements are 1 in a certain bit. And in that case, and is going, if all the bits are 1 in a certain, or if all the elements of A have a 1 in a certain position, then and is going to be 1. But what happens to the XOR in that case depends on whether n is odd or even. And so it made sense to just think about these two cases separately, because in this, if n is odd, then the XOR is 1 in this case, and if n is even, then the XOR is 0. Yeah, and some people are saying we can simplify this by cutting out the choose function and just replacing it with chew to the and getting even just with chew to the n minus 1. Let's see. Why is the answer not the summation of dp of I? So dp is storing the number of ways to fill the first. So dp of I of j is the number of ways to build the first I bits, and so we only want to count the ways that fill all k bits. Wouldn't even odd be? And someone says, wouldn't even plus odd be equal to choose the n minus 1? Yeah. So I basically just use the choose function here because it's something that we can compute quickly. I had template code for it. And so in general, once I sort of have a way that works, I don't. I usually try not to spend any more time than I need to, in order to make the solution marginally faster when I already know it's going to fit into the time limit. And so here, since it's fine to compute, since we have time to compute all these choose functions, I decided to just go ahead and do it because I didn't want to have to work through the math here. Let's see. Someone says, can you think of a pure combinatoric solution? I can for the case where n is odd. For the case where n is even, I know I wouldn't be surprised if one exists, but I don't have it off the top of my head. So it says, can we do this with matrix exponentiation 2 for large n and k? Yeah, so for large n, we need to introduce a bit more combinatorics because then we couldn't compute all these choose functions. But we certainly could, assuming that we could handle that part of things, we certainly could handle a larger value of k using matrix exponentiation. But yeah, I am guessing that that there is a combo way to handle the even case too. I just haven't thought about it. I just haven't really thought about it at all yet. Can you show your choose function template? Yeah, I can. So the first thing I do is I run this initfact, which is short for initialize factorials function, and that's going to compute the factorials of all numbers up to mx, which I just set mx. It's a constant equal to the largest value in the program. So here I just set it to something greater than 200,000. And you'll see I run initfact just in my initialization code down here. And so what I do is is the factorial of I is equal to I minus 1 factorial times I. And then I also compute the inverse of each factorial. And the idea here is of the inverse factorial of mx minus 1 is going to equal 1 divided by 1 times 2 times 3 up to mx minus 1. And so in order to get the inverse factorial of I, we can just multiply the inverse factorial of I plus 1 by I plus 1 because backends of I plus 1 is equal to 1 over 1 times 2 times times I plus 1. And multiplying by I plus 1 just deletes this I plus 1. And so that's going to get us backends of I. And so that gets us our factorials and our inverse factorials of mx time. And then I handle a few edge cases on these first few lines, and that if b is greater, so this computes a choose b, and if b is greater than a, then there's no ways, and if either of these is negative, then I return 0. But otherwise, I just multiply a factorial and then divide by b factorial and a minus b factorial. And this is just the standard choose function formula, a factorial over b factorial, a minus b factorial. And so I'm just computing that using these pre-computed arrays. All right, and so I'm being asked to look at Tour's solution again. Let's take a look. Yeah, so, and someone's saying that it looks like he's doing it without DP. Let's see if I can figure out what's going on here. So, yeah, so my guess is that he's essentially using a similar set of observations to what I've come up with here. But then he's using some combinatorics to skip through the DP step. Someone's saying that you can use Fermat's little theorem to get the first infacts faster. Yeah, I'm sorry. So basically, the reason I don't do anything too fancy is that the bottleneck to running this code is going to be the iterating over these mx values anyway. And so any other changes and so anything that doesn't affect what goes on inside these loops is going to be relatively minor. Yeah, so I'm gonna move on to D just so that we can get to all the problems. So I don't really have time to sort of figure out what this code is doing. That would take me a few minutes to go through off stream. But for now, I'll talk through D and E, and then if people have more questions afterwards, I'll be happy to get to them. All right, so problem D. As at ngrid, So we have a grid of n rows and a billion columns containing only zeros and ones. And a grid is beautiful if and only if for every 2 consecutive rows, there's at least one column containing 1 in these 2 rows. And so we're given the number of rows n and then m segments of the grid that contain 1s. And we have to figure out the minimum number of rows that have to be removed in order to make the grid beautiful. So here's the idea. So this is another DP problem. And so what we're going to say is that dp of I is the maximum number of rows we can keep, such that the last row we kept is row I. And then we can transition from dp I to j if and only if rows I and j contain overlapping segments. So that is, if there's going to be a column containing 1 in those 2 rows. And so if so, then dp of j is going to, we can set dp of j to dp of I plus 1. And in order to compute our answer, there are a couple of ways we can handle this, but the way I do it is I just add row n containing 1s in all positions. And so then the number of rows kept is from the original array is dp of n minus 1, because we're not counting that we're keeping row n. So the number of rows removed is n minus dp of n minus 1, or n plus 1 minus dp of n. And to reconstruct the answer, I just maintain an array last of I, storing the last the last row kept before row I, or before our optimal solution keeping row I. Now this may look like it's O of n squared. In this current formulation, it is. It's going to be far too slow, because here we're talking about transitioning from I to j if rows I and j contain overlapping segments. And in fact, theoretically, if all of the rows contain a 1 in every position, then all the segments could overlap. So we could have O of n squared transitions. Okay, we've got some spam in the chat. Let's see. How do I time out someone? Okay, cool. Looks like it worked. All right. So we have O of n squared transitions. And the way we're going to do this is, the way we're going to get around this is we'll use a segment tree. And the segment tree will store the minimum, and so the idea is that seg of I will store the maximum number of rows that can be kept, such that the last row has a 1 in position I. Then dp of I is going to equal the minimum is going to be 1 plus the maximum seg of j, such that row I contains a 1 in position j. Because that's going to be the maximum number we can keep, such that there's a 1 in a position that overlaps with I. And so what we're going to do is we're going to let seg be a lazy segment tree, so that it supports range updates and range queries. And what we're going to do, essentially, it's going to, the queries are going to be maximum queries, and the updates are going to be of the form set set seg of I to max seg of I, and then a new value v for all I in a range like L through R, for example. And so then what we can do is for each DP value, is for each row, we can query the segment tree once for each segment in that row, and then we can update the segment tree for each segment in that row. And so I'll show you my code to make things a little easier to understand. One nice thing about and so what I do here is I'm going to essentially store pairs of the form dp of I last by, and those are going to go in my segment tree too. And so by default, and so first of all, I'll show you my combined functions in my seg tree. Both of them are just max. And I'm storing the segment tree of pairs of ints. And initially, I set every value in the seg tree to 0, -1. So that means dp of I is 0, so none have been taken, or so no elements have been, or sorry, no rows have been kept so far because we haven't processed any rows yet. And the second value last is -1 to indicate that we haven't taken any, or that we there is no last row. Oh, someone at KK asks, wouldn't segment tree have of 10 to the 9 space complexity? Yeah, I'm glad you asked. So this is where, so what I'm going to do is in order to shrink the segment tree, I'm going to perform coordinate compression. And that's going to, and because there are only 300,000 segments, and each segment contains 2 values, or has like 2 bounds, there can only be 600,000 unique positions in the array, or sorry, yeah, positions, or 600,000 columns, sorry, that are actually distinct in some sense. And so what we're going to do is we're going to perform coordinate compression so that then we're working with coordinates from 0 to 600,000 rather than 1 to 10 to the 9. And so what I do here is first I'm going to create an array A of length n+1. Again, the last value is kind of going to be this fake segment that we're going to create at the end. And then I read in the segments. So I read in x is I, y is L, z is R, and since I'm trying to 0 index, I add y comma z to position x -1. And then I perform coordinate compression on all of the endpoints. And that's going to work similarly to how it did in problem B. So I'm going to create an array vals representing all of the unique values. And it's important that this should only store the unique values. So this is why we don't use a multiset, because we're trying to map the same, we're trying to compress the same value to it, or to the same value every time. And so we're going to put all the values in our set, and then we're going to compress just like we did in problem B. And then to create this fake segment A of n, I'm just going to push back 0 to size of comp -1, which is going to ensure that we're storing everything. Okay, so then I create my DP array, and initially the best value is equal to 0 to -1, and then we traverse we traverse over A to A sub I, and for each of these values we set best to the maximum of best, or the best value on this specific segment. And so then I increase the first value by 1, and that's equivalent to how we are adding 1 in this formula here for dp of I, because remember that the first value is dp of I. And then I set dp of I to best. Then what I do is I update all the segments with best.f, which is dp of I, and then position I, so I is the last position. Okay, and so to reconstruct the answer, I print out n+1 minus dp of n, and then I essentially reconstruct the answer in reverse. So using dp of cur, so I let cur be our current position, and then I look at our last position, which is dp of cur.s, because the second value is equivalent to the last array that I described here. And for each value from next plus 1 to our current value, so for each value in between, strictly in between them, I print that out as one of the values we're removing. And then I set cur to next. And I do this until we reach that -1 default value. Yeah, so Clapdoda says you can get away with compression if you create the seg tree nodes lazily, so you only create the nodes as you need them. Yeah, so that's a technique for those of you who aren't aware known as a sparse seg tree, and that would work here. The reason I didn't do it is that I would worry that that would add that instead of having a log n or log m factor, I guess, we would have a log 10 to the 9 factor. And so that would make the constant factor of the program a little worse, which could potentially be problematic if the time limit were tight. And the other reason I didn't do it is because I don't have a template for sparse lazy seg tree. So yeah, so that's why I just did that. I just did this as a regular lazy seg tree with coordinate compression. And of course, the coordinate compression code is pretty quick to write, so it wasn't too much of a pain. All right, great. So that handles D. Let's move on to E. So we're given an 8x8 chessboard, and we get to place a queen on a position of our choosing. So on any given turn, we can move the queen, we can perform any sort of queen move, and then the king is going to move afterwards. And the king cannot move into a cell occupied, or that is on the same row, column, or diagonal as the queen. And in particular, unlike in regular chess, the king cannot capture the queen. Which I guess actually would be impossible anyway, but yeah, the king can't move onto the position of the queen or onto any cell checked by the queen. So we're going to make up to 130 moves. The queen is just going to move around the board, and then the king is going to try to evade them. And each move is going to be made, and so we're going to make each move, and then the king is going to move, and we have to checkmate the king within 130 moves. And if after 130 moves the king still has valid moves, then we're going to then we lose and we get WA. All right. So the first thing that I think is helpful here is to think about how the queen can checkmate the king. And what I'm going to show you here is that the queen can only achieve checkmate if the king is backed up against a wall. And so let's say, for example, that we have this queen I'll represent using a circle and a king I'll represent using an X. Then if we move the queen into a position next to the king and the king doesn't have a wall behind it, then the king can just move backwards away from the king, away from the queen, and then outside of the row of the queen. So in this case, the king can move to position X, or to this position here, or this position here. And so if the king is not against a wall, then it can be checkmated. On the other hand, if the king is against the wall and the queen is, and in particular if the king is between the queen and the wall, then the king is checkmated. We can verify that there are no valid moves in this situation. And in particular, we can verify that this sort of situation where the king is between the queen and a wall is the only way we can create a checkmate. And if you ask, will this live stream be archived? Yeah, it will. It'll be on my channel after it finishes. Okay. So that should sort of make some sense. We're trying to push a queen up against a wall. The king up against a wall. And so there were a number of ideas I tried before I eventually figured out the one that worked. But essentially the way I thought about this is I'm going to maintain the set of positions where the king could possibly be. And initially I just decided, okay, let's just place the queen in the top left. So let's say we have the queen up here. Then the king cannot be in any of these positions in this row or column. Oops, because the queen would be checking it. So that means that the king has to be somewhere in this box here. And in fact, it also can't be on this diagonal, but I'm not going to worry about that for now. So we have the queen up in this top left corner and the king in this box. Now, what happens if we move the queen down? So we go down here. Now then, what could happen is the king is the so first of all, the king could end up below the queen, or the king, if it was in this top row already, could move up. And so we end up in a configuration like this. But this is actually really good for us, because if this is the top column, then now what we can do is we can just go around putting the king in, or we can just go around and put the king in checkmate if it's in any of these positions. So for example, if our next move pushes the queen to this position, then if the king is here, then it's checkmated now. And so then that means that we have that the setup now looks a little like this, where and so then we can move the queen to the right again, and we can checkmate the king if he's currently standing here. And so again, the set of possible positions is going to shrink. And in general, we can checkmate all of these positions, the entirety of this row, in at most in like under 8 moves. And then we have one fewer row to deal with. All right, so that's how I thought about starting out, and so then I decided to try and generalize this approach. So here's the idea. What I'm going to do is I'm going to maintain a list of possible positions for the king. And so then I'm repeatedly going to enter the following process. So first, I'm going to pick a cell where the king could be to target. And this is going to be, and basically what I'm going to do is I'm going to say, all right, if the king is currently in this position, I'm going to checkmate it. And so let's say I, the queen, am like up here, and our target is, I don't know, somewhere down here. So the next step is I'm going to move to the target's row. So I'm going to move down here. Now the target is going to have to move away. So it's going to be either in this column, or either in this row or this row. Let's say for the sake of argument that it's going to move down. So let's say it goes here. Then I'm going to move to the target's column. And I'm going to go over here. And now the king is going to have to move away. It's going to have to move away from me. And so it can either go to this position or this position. And let's say it goes here. And now I'm going to use diagonal moves to chase the king until it hits a wall. And so what I mean by that is I can move one down and one to the right to get to this position. And then the king is going to again have to move backwards. Let's say it goes here. So then I'm going to use diagonal move to get here, and then the king is going to have to move backwards again. And I can use that process to get, to push the king against the wall. Now, here's the key idea and the key reason that this approach does end up working. The idea is then we can checkmate the king, but we can also checkmate any remaining starting positions within this row. And what I mean by that is that it's like, if, for example, it might be so in this situation, hypothetically, it could be possible to have that the king could be in some of these other positions. So it might be that the king could be in that, like, all of these are possible positions for the king. I guess not all of them, because some of them are diagonal to the queen, and that would be bad. But But let's just say we could have other other positions where the king could be right now. And after we checkmate the target, then we can checkmate all the other possible positions in the target's row. And so there's going to be one fewer row where the king could be. So there are at most 8 such cells. So after at most 8 moves, there is one fewer row where the king can be. And we can also bound the number of steps in this chasing process, because this is going to be one step, this is going to be one step, and we can prove that this is going to be at most 6 steps, because in the worst case, we have, let's say the queen starts in the top row here, and the king starts in the next row here, then the king can only move down 6 times. And so there are only 8 rows, so we have at most 8 times we perform the following steps. We can chase, which takes up to 8 steps, and then we can checkmate the row, which takes up to 8 steps. And so in total, there are most 16 steps per cycle, and in fact this bound isn't quite tight, but it's good enough for our purposes. So at most 8 times 16, or 128 steps overall. And that's 128 is less than 130, so this is a valid solution. So I'll go through my code now. So I actually wrote a number of helper functions here. So first of all, I have this pair of ints target that just represents the current target. I just initialized it to something ridiculous. And this array OK, which stores the possible positions for the king. Then I have these dx and dy helper arrays that store the possible moves, like for the queen, or the possible one-step moves for the queen. And so, for example, dx of 0 is 1, 1. That represents going down 1 and to the right 1. I also have this valid function that checks whether a pair x, y represents a valid position in the chessboard. Then I write these functions get x and get y to represent the change in x and the change in y corresponding to a certain move. So for get x, what I do is essentially if s contains left, then I say, okay, we're decreasing x by 1. If it contains right, then we're increasing x by 1, and otherwise we're not changing x. And then a similar thing for y. Then I have this update function, and this basically updates the state of the game if the queen is now at position x, y, and the velocity that the king just took is v. And so I build this array next that's going to store the new possible positions for the king. And I basically say, okay, if I, j is a valid position that is currently a possible king location, and the new position, nx, ny, is a valid position on the chessboard, then nx, ny is reachable. And so I update OK, and then the other thing I do is I build a list of all of the positions that can be reached by the queen. So I basically multiply the 8 queen moves by all the values from 0 to 8, and I say, okay, these are not possible king positions because the king cannot have moved next to the queen, or within the reach of the queen. And so then this is my function that performs a query. So to query x, y, my positions are 0 indexed, so to get them 1 indexed, I output x plus 1 and y plus 1. Then I read in the result. And if the result is done, then I return true because we're done with this test case. And otherwise, I actually swapped x and y when I was initially thinking about the problem, so I have the swap function here, but I get the velocity vector. I update the position of the target, and then I update the state of the board and return false. Then this get first function, this just gets the first position that's currently valid, and if there is no such position, I assert false because that should not be happening. So then we get into my main function, and so what I do is I initially set x and y to 0, And then I maintain the state variable that stores our current step in this process. So if state is 0, then we need to move to the target's row. If state is 1, we move to the target's column. And otherwise, we use our diagonal moves. So the idea here is while the current, or if first of all, if the target is not a valid position, not at a valid position, or if it's not a possible position for the king, then I say, okay, we've checkmated this target, so let's set a new target. Then I say, okay, first of all, if the target is in a position that can be checkmated, then we're going to checkmate it by moving to its column. Otherwise, if our state is 0, I'm going to set x to the then I'm going to move to its row by changing x. If our state is 1, then I'm going to do this step, moving to its column. And otherwise, this step just performs the chasing operation. And I do this all while our query does not say we're done, and that gets us our solution. Let's see, I think I actually made a slight error in implementing this, and I'm kind of curious if that's going to lead to an FST, because I think I actually need to prioritize targets that are in row 7. Because I need to prioritize targets that are in row 7 in my getFirst function when I'm selecting a new target, because otherwise I might just say, okay, I push a whole row down to row 7, but then now afterwards I'm in a bad position because I'm only going to checkmate one of the targets, and then I'm going to just pick a new row entirely. And so that messes with my complexity here. So I'm actually kind of curious. I can modify that quickly in my code just by doing I plus 7 mod 8, and I'm kind of curious whether I FST'd because of that. Let's check. No, looks like I didn't. Okay, I'm kind of curious if there's a way to prove that my solution still works, but for now it looks like I'm good to go. Kleptota says this is different from his proposed solution. I'm curious, what was your, do you want to share what your idea was? I'd be sort of interested to see what the other options are. And in the meantime, I think that's all of the explanations done, so if anyone has any questions, I'd be happy to go ahead and answer them. See, wonder if the editorial has been posted. I'm curious if there were other solutions that are different from what I did. Doesn't look like it's out yet. All right, well, I'll give everyone a moment longer. I put a paste-bin link, but I think YouTube hides links or something. Okay, that's unfortunate. But yeah, I'm not surprised that there are multiple ways to do this. I sort of did this by, when I sort of did this problem, I was kind of just trying a bunch of different things until I figured out one that worked, and that worked in a way that was easy enough for me to formalize that I could implement this without it being a huge pain. So, I don't think there's any reason a priori to believe that like this solution is going to work. I don't think it's as motivated as my solutions to some of the other problems. This feels like much more of a matter of just trying things until you find a way that works. But yeah, it was a fun problem. Thanks for sharing it. It's interesting to me because just because this seems like something that, I guess it's not really a standard chess situation, because normally, first of all, the king would be able to capture the queen, so this mating position that I've set up where you back up the king against a wall wouldn't work because the king would just capture the queen. And normally you would also have a king of your own to help capture their king. So, but it is interesting to me just because it's a relatively simple scenario, and yet, it works out to be a pretty interesting problem that works as a div2e. And like a reasonably, not a trivial one, because there were 60 solves, which is not that many. And how many in div2? Yeah, 7. I actually thought overall this contest had a very nice difficulty curve. I do think the time limit on A maybe should have been 2 seconds because it TLEs people who read in the integers as doubles, which is I mean, it's obviously a silly thing to do, but on the other hand, like constant factor TLEs are maybe not great. But yeah, I mean, overall, I think the round was good, pretty well prepared, fun problems. So yeah, let's see. Purple Crayon says, "Is it possible to hack E?" I actually don't know. That's an interesting question. There isn't anything related to hacks on here, so I actually don't know. Yeah, that's a good question. A Tonal Pancake asks, "How can you share some info on how a beginner can get good enough to participate in programming contests?" It basically comes down to learning a programming language of your choice, and there are a lot of good books and videos on learning to program. I don't have a particular one that I'd recommend just because it's sort of been a while since I used any of them, and I don't feel like any of the ones I used were really perfect resources. If anyone else has some suggestions, please feel free to share them in the chat. But I would say just find a book or a video depending on your preference, and watch it. And you don't need to learn anything super advanced. I think to get started, you mostly just need to learn concepts like input and output, obviously, loops, conditionals, so if statements, arrays, writing methods, that sort of thing. And a lot of the programming techniques you can you can learn as you go. And so once you have a basic idea of how to program, then you can start working on Codeforces problems, and it could be a pretty slow start depending on your level of math background, but if you just stick with it, you'll find that a lot of the techniques repeat themselves between problems, and so the more problems you solve, the easier it'll become. Decoder says, "Which extension do you have for showing delta?" I use Caret. It's nice on a number of levels. I think first of all, I found that it generally is more accurate and up to date than CF Predictor is, and it also shows performance levels that you would need to achieve a 0 delta at a given position, and so it's helpful when I want to see like how well I would have had to do on a contest to gain rating. Someone asked to check the problem B solution of Tourist. I'd encourage you to watch the stream archive once I finish up here, because this I took a look at it earlier on in the stream. Wanted to mention that clicky keyboard is satisfying. Yep, that is actually a comment I get on a fairly regular basis, and I'm pretty confident that my keyboard is responsible for more of my subscribers than my programming contest experience. But and you know what? I can live with that. We'll deal with it. But yeah, I think that is about all that I have. If anyone has any final questions, then I can answer them real quick. But otherwise, I appreciate you all for coming out here, and please, thanks for watching, and please feel free to leave any questions you have in the comments on YouTube. Someone asked, "Why is problem B tagged as bitmask?" I do not know. A lot of the time, the tags initially are relatively arbitrary until some of the spam gets cleaned up a little. Alright, I think that's all for now. So I will see you guys next time.